The universe was completely dark for millions of years. Then the first stars switched on. That initial spark of light did more than just pierce the darkness. It ignited a chain of events that led to everything we see today, including us. But what if that first light holds secrets that could rewrite our entire cosmic history? We are about to embark on a journey to the very edge of time, to explore 30 of the greatest unsolved mysteries from the dawn of creation. By the end, you will understand the profound and unanswered questions about how our universe grew from a simple, dark void into the complex, star-filled cosmos we call home. We will ask what the first stars were made of and how their explosive deaths may have planted the seeds for life. What do you think it took for light to finally conquer the ancient dark? That initial light came from a type of star we have never actually seen. The very first generation of suns is called Population 3. This name might sound technical, but it tells a profound story. Astronomers classify stars into populations based on their ingredients. Our own sun is a population 1 star, rich in heavy elements like carbon, oxygen, and iron. Older stars in the halo of our galaxy are population 2, with far fewer of these metals. But population 3 is the ultimate ancestor. The theory is that these first stars formed from the pristine gas of the early universe, a soup composed of only 2 elements, hydrogen and helium. Nothing else, no silicon for rocks, no oxygen for water, no iron for blood. They were pure and elemental, and this purity may have made them utterly unlike anything that shines in our night sky today. Because they lacked the complex chemistry that helps modern gas clouds fragment, the first stars might have grown to staggering, almost unimaginable sizes. Current models suggest they could have been monsters, hundreds of times more massive than our sun. Picture a single star so large it could swallow our entire solar system. With such immense mass came ferocious power, burning their nuclear fuel at a breakneck pace. Their lives would have been spectacularly short and violent, perhaps lasting only a few million years. For comparison, our sun will live for roughly 10 billion years. These cosmic giants were here in a flash, and their deaths were as extreme as their births. A star that massive faces a dramatic end. Some might have exploded in supernova of such staggering energy that they dwarf anything in the modern cosmos, completely obliterating themselves and seeding the surrounding void with the first heavy elements. Others might have bypassed the explosion entirely, their cores collapsing directly into black holes, vanishing from the visible universe without that final flash. This is the central puzzle. We have never directly spotted a single, true population 3 star. They flickered on and died in the universe's deepest infancy, too far away and too brief for our telescopes to catch in the act. So how do we hunt for ghosts? Astronomers search for their chemical fingerprints. The idea is that the violent deaths of these first stars polluted the early cosmos. We look for that pollution. In the light of the most distant quasars, beams from the dawn of time, we analyze the faint absorption lines in their spectra, hoping to find the signature of gas enriched only by the first supernova. Closer to home, we study the most ancient stars in our own galaxy, ancient population 2 stars that are incredibly metal-poor. Their atmospheres are like cosmic archaeology sites, preserving the elemental abundance patterns from a single, or perhaps a few, population 3 supernova. By decoding these patterns, we are trying to read the recipe of the very first stardust. What would it mean if we found proof that these giants were real? It would confirm the origin story of every element that makes up our world and ourselves. But those first stars did more than just create new elements. Their brilliant, ultraviolet light began a universal revolution. For nearly 200 million years after the Big Bang, the cosmos was a neutral fog of hydrogen gas. This period is called the Cosmic Dark Ages. Then something happened. A great flood of energetic radiation swept through the universe, tearing electrons away from those hydrogen atoms in a process we call reionization. This event cleared the fog, making the cosmos transparent to light and ending the darkness forever. It is one of the most important transformations in cosmic history, and we still do not know exactly what caused it. The prime suspects are the first stars and galaxies. Their intense ultraviolet light is a powerful ionizing force, but was it enough? The sheer scale of the problem is staggering. To reionize the entire universe, you need an enormous number of these energetic photons, and they need to escape their host galaxies to travel vast distances through intergalactic space. This leads to a deep mystery. Did the dominant source come from those massive, short-lived population 3 stars, from the collective output of countless smaller early galaxies, or from something even more exotic, like the first supermassive black holes powering brilliant quasars? Each source paints a different picture of the early cosmos. If massive stars were the main driver, it means the first galaxies were incredibly efficient at producing and expelling this harsh light. If early quasars dominated, it suggests black holes grew to immense sizes with astonishing speed. Modeling this epoch is incredibly difficult because it involves the complex interplay of light, gas, chemistry, and gravity on a cosmic scale. We are essentially trying to solve a puzzle where most of the pieces are hidden. This is where the James Webb Space Telescope becomes our greatest detective. By peering back to when the universe was only a few 100 million years old, Webb is searching for the faint, infant galaxies that might have provided the radiation. It is measuring their numbers, their brightness in specific ultraviolet bands, and crucially, whether their light shows signs of leaking out into the void. Every new, distant galaxy Webb finds is a potential suspect in this cosmic mystery. By mapping the timeline of reionization, we hope to discover what finally lifted the veil on the universe, allowing the story of stars and galaxies to be written across the clear, dark sky we see today. That pristine hydrogen and helium gas held a problem. In our modern universe, gas clouds collapse to form stars because they can cool down. Complex molecules like carbon monoxide and dust grains radiate heat away, allowing dense knots to form and contract under their own gravity. But in the beginning, there were no molecules, no dust, no heavy elements at all. The only coolant was the hydrogen itself, and it is terribly inefficient. So how did the first star overcome this thermal barrier and begin to shine? The answer lies in the invisible scaffolding of the cosmos, dark matter. After the Big Bang, dark matter began to clump together under its own gravity, forming vast, diffuse structures we call dark matter halos. These halos are like gravitational wells, and they are key. Ordinary hydrogen and helium gas drawn in by the halo's pull would accumulate at its center. As this gas became denser, it would eventually start to heat up from the sheer pressure of collapse. But here, the simple hydrogen gas found a way. At extremely high densities, the hydrogen molecules can do something special. They can collide and vibrate in a way that converts their gravitational energy into infrared radiation, which then escapes into space. This process, known as molecular hydrogen cooling, was the universe's first air conditioning system. It was weak, but it was just enough to allow the hot, dense cloud at the heart of a dark matter halo to lose a critical bit of heat and continue collapsing. This is where the mystery of fragmentation takes center stage. In today's star-forming clouds, cooling is so efficient that the cloud shatters into countless fragments, producing a whole cluster of stars of various sizes. But in those first halos, with only this rudimentary cooling, the physics is radically different. Did the cloud fragment at all? Supercomputer simulations, which model the behavior of millions of particles of gas and dark matter over millions of years, give us a glimpse but not a definitive answer. Some simulations show the primordial cloud collapsing into a single, massive disk that then breaks apart, perhaps forming a small handful of truly gigantic sibling stars. Others suggest it remains a monolithic structure, funneling nearly all of its gas down to one central point, birthing a solitary leviathan. The uncertainty is huge because these simulations operate at the very edge of our computational power and physical understanding. Tiny changes in the starting conditions or in how we model the gas chemistry can lead to wildly different outcomes. We are essentially watching the birth of the first light in the universe through a computational keyhole, seeing only hints of the true, majestic, and violent process. The formation of that very first star was not a gentle gathering of dust. It was a desperate, slow-motion battle against heat and gravity in a silent, elemental universe, and we are still trying to witness how it was won. Their spectacular deaths were as important as their brilliant births. When these first stellar giants finally exhausted their nuclear fuel, they did not fade quietly. They detonated with a violence that shaped the future of the cosmos. But the nature of that final explosion is a deep mystery because the type of supernova depended entirely on the star's initial mass. For the most massive of the first stars, those between about 140 and 260 times the mass of our Sun, physics dictates a uniquely terrifying end. In their cores, the temperature becomes so phenomenally high that light itself begins to behave like matter. Pairs of electrons and their antimatter counterparts, positrons, spontaneously pop into existence. This process, called pair instability, robs the core of the pressure holding it up against gravity. The result is a runaway collapse followed by a thermonuclear explosion of unimaginable scale. In a pair instability supernova, the entire star is utterly annihilated. No black hole, no neutron star remains. The star is completely turned inside out, blasting all of its newly forged heavy elements, carbon, oxygen, silicon, and iron, out into the void. It is a complete recycling event, a cosmic reset button that leaves nothing behind but an expanding cloud of enriched gas. For slightly less massive first stars between roughly 10 and 140 solar masses, a more familiar but still extreme fate awaited. These would have died in core collapse supernova. Here, the star's iron core catastrophically implodes, then rebounds in a shockwave that blows the outer layers away. But even this familiar story has a primordial twist. Without heavy elements to carry away energy, the shockwave might have struggled to escape, leading to unusually energetic or oddly shaped explosions. The crucial difference is that a core collapse supernova leaves a remnant behind either a dense neutron star or a black hole, while still ejecting a significant portion of its elements. So which type of death was more common in the infant universe? The answer dictates the chemical legacy of the first stars. Pair instability explosions would have flooded their surroundings with a very specific mix of elements, rich in certain isotopes like silicon and calcium, but perhaps lacking others. A core collapse event produces a different chemical signature, and critically, it leaves behind those compact remnants that could later merge or grow. Our entire galactic neighborhood might have been built from the specific pattern of debris from one type of explosion over the other. To solve this, astronomers act as cosmic chemists. They look at the oldest stars we can find, those population 2 stars in our galaxy's halo. The elements in their atmospheres are like a fossil record of the very first supernova that polluted their birth cloud. By measuring the precise ratios of elements, how much carbon there is compared to iron, or the abundance of strontium, they can match the pattern to a theoretical model of one type of explosion or the other. Early data suggests hints of both, implying a wild diversity in those first deaths. Some ancient stars show the clean signature of a single, enormous pair instability event. Others seem to bear the imprint of multiple, smaller core collapse explosions. This means the first chapters of cosmic chemical enrichment were not written with a uniform pen. They were scrawled in the chaotic, brilliant script of stellar explosions of every conceivable scale, each one seeding the darkness with the very ingredients that would, billions of years later, form rocky planets, flowing water, and living beings. The fate of the first stars was not just an end, it was the first step in a recipe we are still trying to decipher. Those violent deaths left behind more than just chemical seeds. For the most massive first stars that avoided a pair instability explosion, their final act was a total gravitational surrender. The star's core, having fused elements all the way to iron, would suddenly have no outward pressure left to fight the crush of its own immense weight. In a catastrophic instant, it would collapse past the point of no return, vanishing from the visible universe and leaving behind only its gravity, a black hole. This is how the very first stellar mass black holes were likely born, the primordial remnants of the first generation of stars. But here, the mystery deepens into something far grander. Could these specific black holes, forged in the universe's first moments, still be lurking around us today? And could they, astonishingly, be the very fabric of dark matter itself? The idea is radical. For decades, the leading candidates for dark matter have been exotic, undiscovered subatomic particles. But an alternative theory suggests that some, or even all, of the invisible mass holding galaxies together could be vast numbers of these ancient black holes, each one perhaps tens of times the mass of our Sun, scattered like invisible ghosts throughout the cosmos. They would be perfectly dark, nearly impossible to see, and their collective gravity would match the effects we attribute to dark matter. This makes them a compelling, if elusive, target. The hunt for these primordial black holes is a detective story that uses the fabric of space-time itself as a tool. One method looks for their subtle, fleeting fingerprints on light. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, bending and magnifying the star's light for a brief period. Astronomers scan millions of stars in nearby galaxies like the Magellanic Clouds, searching for these characteristic brightening events called microlensing. The duration and shape of the brightening tell us about the black hole's mass. So far, these surveys have largely ruled out primordial black holes making up all of dark matter in a certain mass range, but the search continues for heavier or lighter suspects. A more dramatic signature comes from collisions. If two of these ancient black holes were to spiral together and merge, they would shake the very foundation of space-time, sending out ripples known as gravitational waves. Our observatories like LIGO and Virgo have now detected many such mergers. The key question is, are these black holes the descendants of more recent massive stars, or are they primordial relics from the dawn of time? Scientists scrutinize the masses and spins of the colliding black holes for clues. A population with very similar and surprisingly high masses could point to a primordial origin, a batch of objects all forged under the same unique conditions in the early universe, rather than the diverse outcomes of later stellar evolution. Finding even one confirmed primordial black hole would be a monumental discovery. It would open a direct window into the physics of the first stars and their deaths, and it could fundamentally reshape our understanding of what dark matter is. We are listening for their collisions and watching for their shadows, searching for the silent, gravitational echoes of the universe's first catastrophic endings. This timeline is not just a date on a cosmic calendar. It is the answer to a profound question: how long did the universe wait in darkness before its first dawn? Our best estimates suggest the first stars flickered on somewhere between 100 and 200 million years after the Big Bang. We arrive at this range through two powerful lines of evidence. The first is the cosmic microwave background, the afterglow of creation itself. By mapping its faint temperature fluctuations with exquisite precision, satellites like Planck have measured the state of the universe when it was only 380,000 years old. This data tells us when the cosmic fog was thickest, and from there we can model how long it took for gravity to pull together the first structures dense enough to ignite stars. The second line of evidence comes from pushing our telescopes to their absolute limits. We search for the most distant, and therefore the earliest, galaxies we can possibly detect. Each one we find is a data point, a candle lit at a specific moment in cosmic time. By finding galaxies that existed when the universe was only 400 or 500 million years old, we can work backwards, asking how long it must have taken for their ancestors to form. The challenge is that the very first stars were likely not part of grand, bright galaxies. They were isolated beacons in an immense, dark void, far too faint for any telescope to see directly. So we are forced to infer their birth by studying their slightly older, more developed descendants. This creates a deep uncertainty. Did stars begin to form in a sudden, widespread flash, like a cosmic wildfire catching across the void? Or was it a more hesitant, piecemeal process, with isolated pockets of light struggling to emerge before slowly multiplying? The answer defines the character of the universe's infancy. A rapid onset suggests the conditions for star formation were met almost universally once the cosmic gas cooled sufficiently. A slower, more scattered beginning implies that the first stars were rare anomalies, dependent on exceptionally lucky configurations of dark matter and gas. This is where the James Webb Space Telescope is rewriting the story. Its mission is to push the observational frontier back to within 200 or 300 million years of the Big Bang, deep into the era when the very first galaxies were assembling. Every time Webb discovers a galaxy that is brighter or more developed than our models predicted for such an early time, it sends a shockwave through cosmology. It forces us to ask, did the first stars ignite even earlier than we thought? If galaxies were already large and complex only 250 million years after the Big Bang, then the seeds for those galaxies, the first stars and their dark matter halos, must have begun forming shockingly soon. Each new, ancient galaxy Webb finds is like finding a sophisticated city in what we believed was a barren wilderness. It compresses our timeline, suggesting the universe moved from simple darkness to complex light with a speed and efficiency we are still struggling to understand. The exact moment of first light is more than a number. It is the benchmark for the universe's creative potential, a measure of how quickly chaos can give birth to order and darkness can give way to a story. The assembly of the first galaxies is a story of cosmic architecture. We have these brilliant, massive first stars, but they were likely isolated giants. How did they come together to form the first structured cities of light? The prevailing theory is a slow, bottom-up process called hierarchical assembly. In this model, small dark matter halos, each perhaps hosting a single massive star or a small cluster, would drift together over hundreds of millions of years. Their gravity would pull them into mergers, building up larger and larger structures. It is a gradual, bottom-up construction, like building a metropolis by first assembling neighborhoods and then linking them with roads. This process seems logical, and we see evidence of it throughout the later universe. But when we point our most powerful telescopes to the very edge of observable time, the story gets complicated. The galaxies we see there when the universe was less than 500 million years old appear surprisingly bright and mature. They seem too developed, too massive, to have been built solely through the slow merging of tiny pieces in such a short cosmic time. This discrepancy forces us to consider a radically different top-down possibility. Could some of the first galaxies have formed almost whole in a single, rapid collapse? This leads us to one of the most intriguing theoretical ideas in modern cosmology, the direct collapse galaxy. Imagine a scenario where two large streams of pristine gas flowing along the filaments of the cosmic web collide head-on. Instead of fragmenting into countless stars immediately, the gas loses its spin and angular momentum in the violent collision. It forms a vast, turbulent, and incredibly dense cloud that is stabilized against fragmentation. This immense reservoir of gas, perhaps containing the mass of billions of suns, could then funnel directly toward the center of a massive dark matter halo. There, in the heart of this chaotic nursery, something extraordinary could happen. the gas might collapse so rapidly and with such force that it bypasses widespread star formation entirely. Instead, it could coalesce directly into a supermassive black hole, a monster with a mass millions of times that of our Sun, all before the galaxy around it has even lit up with its first significant generation of stars. This is not a gradual build-up, it is a cosmic shortcut, a genesis event where the central engine of a galaxy forms first and the stellar city builds around it later. The role of dark matter in all this is absolutely fundamental. It provides the gravitational anchor, the deep well that pulls in the ordinary gas. The shape, mass, and merger history of a dark matter halo dictate everything about the galaxy that forms within it. A quiet, isolated halo might foster slow, bottom-up growth, but a halo sitting at a busy intersection of cosmic filaments, experiencing major mergers or massive gas inflows, could be the perfect site for a rapid top-down collapse. The observations from the James Webb Space Telescope are now the ultimate test. When Webb looks at these ultra-distant galaxies, it is not just counting them. It is analyzing their shapes, their masses, and crucially, the light from their centers. Is there already the glaring signature of a supermassive black hole, a brilliant quasar shining at the heart of a galaxy that is otherwise still assembling? Or do we see only the collective light of billions of young stars, suggesting a more traditional, bottom-up origin? Each new data point is a clue in this architectural mystery. Were the first galaxies built brick by brick, or did some of them emerge nearly complete from the cosmic forge, with a dark heart already beating at their center? The answer will tell us if the universe's first structures were patient constructions or miraculous, rapid-fire creations. The brilliant light of a distant quasar is more than a beacon. It is a cosmic probe shining through billions of light-years of intergalactic space on its journey to our telescopes. When we break this light into a spectrum, we see something astonishing. Instead of a smooth rainbow, the quasar's light is carved up by thousands of sharp, dark absorption lines. This dense, intricate pattern is known as the Lyman alpha forest, and it is one of our most powerful tools for mapping the invisible architecture of the young universe. Each one of those dark lines is a fingerprint. It marks a specific point along the line of sight where a cloud of neutral hydrogen gas has absorbed a precise wavelength of the quasar's ultraviolet light. Because the universe is expanding, clouds at different distances are moving away from us at different speeds. This stretches the wavelength of the absorbed light, shifting each line's position in the spectrum. By measuring these shifts, we can map the location of every hydrogen cloud between us and the quasar. It is like taking a core sample of the cosmos, revealing a layered fossil record of its structure across time. The mystery lies in reading this record to understand the epoch of reionization. As the first stars and galaxies turned on, they created bubbles of ionized, transparent gas within the vast neutral fog. Imagine a block of Swiss cheese where the holes are these growing bubbles of light. The Lyman alpha forest allows us to see the cheese. By studying quasars at different distances, we look back to different eras. If we see a nearly complete forest at a certain distance, it means the line of sight is still passing through mostly neutral gas. The reionization bubble hasn't reached there yet. If the forest suddenly disappears or becomes sparse, it means the light is traveling through a fully ionized region. The fog has cleared. The grand puzzle is deciphering the pattern of this clearing. Was reionization a swift, uniform process, like a rising tide that lifted the fog evenly across the entire universe? Or was it a slow, patchy affair, with islands of stubborn neutral gas persisting long after their surroundings were flooded with light? The Lyman alpha forest holds the answer, but it is a complex code to crack. The challenge is that the process itself changes what we see. Early in reionization, the neutral islands are large and the forest is thick. As bubbles grow and merge, the remaining neutral gas gets confined to ever smaller, isolated patches. This creates a specific signature in the absorption lines. A uniform reionization would leave a sharp, clean edge in the forest at a specific cosmic time. A patchy one would show a gradual thinning over a much longer period. Current observations from the most distant quasars suggest the process was indeed extended and messy. We see evidence that some regions were cleared of neutral hydrogen surprisingly early, while others held out for hundreds of millions of years longer. This patchiness tells us that the first light sources were not evenly distributed. The universe's Great Awakening was a chaotic, local affair, with brilliant oases of ionizing radiation slowly burning away the primordial dark, one region at a time. Decoding the Lyman Alpha forest is like listening to a symphony of shadows, each note a whisper from a cloud of gas that hasn't existed for over 12 billion years, all to understand how the light finally won. This intricate map of the early universe leads us to a mystery much closer to home, one that pits our most sophisticated simulations against the reality we see outside our galactic window. Modern cosmology faces a glaring discrepancy known as the missing satellite problem. When scientists run supercomputer simulations of how dark matter should clump and structure the cosmos, they produce a very specific prediction for galaxies like our Milky Way. Our galaxy should be surrounded by a vast swarm, thousands of smaller dark matter halos, each one a potential home for a tiny, orbiting dwarf galaxy. Yet when we look, we find only a few dozen of these faint companions. The question is stark: where are all the rest? This is not just a minor accounting error. It is a fundamental tension between our theory of dark matter and the actual history of star formation in the smallest cosmic structures. One compelling solution brings us right back to the violent nature of the first stars. Imagine one of those predicted small dark matter halos in the early universe. It manages to pull in a cloud of pristine gas, and within it, a single massive population 3-star ignites. This star lives fast and dies young, and its death is catastrophic. In a supernova of unimaginable power, it blasts its outer layers into space. For a small halo with weak gravity, this explosive energy is a disaster. The supernova can literally blow away all the remaining gas from the halo, ejecting it into intergalactic space. Without gas, there is no fuel to make new stars. The dark matter halo remains an invisible ghost of potential, but it is now dark forever. It becomes a failed galaxy, a satellite of the Milky Way in gravity alone, with no stars to light its presence. This process, where early stellar feedback sterilizes small halos, could explain why we see so few dwarf galaxies. The first generations of stars were not just creators, they were also cosmic sensors, shutting down star formation in the smallest neighborhoods before it could truly begin. But this is not the only theory. Another possibility lies in the very nature of dark matter itself. The standard cosmological model uses what is called cold dark matter, particles that move slowly and clump easily. But what if dark matter is slightly different? Warm dark matter is a hypothetical variant where the particles are lighter and faster. This slight change has a dramatic effect on the smallest scales. Warm dark matter would suppress the formation of those very tiny halos from the start, resulting in a universe with far fewer small structures, neatly matching the observed count of dwarf galaxies. The hunt to solve this mystery is a two-front war. Observers are using ever more sensitive telescopes to search for the faintest possible dwarf galaxies, pushing the limits of what is detectable. Every new, ultra-faint satellite discovered helps complete the census. Meanwhile, theorists are running increasingly detailed simulations that model not just dark matter, but also the complex physics of gas, stars, and supernova with incredible precision, trying to see if the explosive feedback from the first stars is truly enough to leave thousands of halos in permanent darkness. The answer will tell us not only about the environment of the early universe, but about the fundamental rules that govern the invisible scaffolding of all reality. Did the first stars leave behind a legacy of dark, silent halos as their final act? Or must we rewrite the recipe for dark matter itself to understand our local cosmic neighborhood? The missing satellite problem hints at a universe where small structures were suppressed, but at the other extreme of the cosmic scale lies an even more pressing mystery. At the very centers of galaxies, including our own, lurk supermassive black holes. These are not the stellar remnants of dead stars. They are monsters with masses ranging from millions to billions of times that of our Sun. Their existence in the modern universe is astonishing enough, but their presence in the infancy of the cosmos is a crisis for physics. We have now observed incredibly bright quasars powered by supermassive black holes, shining from a time when the universe was just 700 million years old. To grow to such staggering sizes so quickly, these black holes had to start from something, and they had to eat at a rate that defies our current understanding. This is the race against time at the dawn of creation, and we are still searching for the starting line. The leading theories for the origin of these cosmic giants all point back to the unique conditions of the early universe, but they follow very different paths. The first idea connects directly to the first stars. Perhaps the very largest population 3 stars, those pushing the upper limits of mass, did not explode at all. Instead, their cores could have collapsed directly, leaving behind a black hole seed of perhaps a few hundred solar masses. This is a substantial head start compared to the 10 solar mass black holes from later stars, but it is still just a seed. For this seed to grow into a billion solar mass quasar in only 700 million years, it would have to consume gas at the maximum possible rate, almost continuously for its entire existence. This is like trying to grow a giant sequoia from a sapling in a single human lifetime, requiring perfect, unbroken conditions for growth. The second theory suggests a more dramatic beginning, the direct collapse black hole. This skips the star entirely. Imagine a massive, pristine cloud of gas at the center of an early dark matter halo. As we discussed, without the cooling agents provided by heavy elements, this cloud might resist fragmenting into many stars. Instead, it collapses in on itself as a single, monolithic entity. The result could be a supermassive star, a behemoth tens of thousands of times the mass of the Sun, that lives briefly before its core collapses. This creates a black hole seed that is already tens of thousands or even 100,000 solar masses from day one. This is not a sapling, it is a fully grown tree suddenly appearing in the forest. With such a massive head start, the pressure to grow to quasar proportions is slightly less extreme, though still formidable. The final piece of the puzzle is the feeding frenzy itself, a process called accretion. A black hole grows by pulling in surrounding gas. As this gas spirals inward at tremendous speeds, it heats up to millions of degrees, glowing brilliantly before vanishing across the event horizon. This is what powers a quasar, but there is a limit to how fast a black hole can eat, known as the Eddington limit. It is a balance between the inward pull of gravity and the outward pressure of the radiation the infalling gas produces. If the black hole eats too fast, the intense radiation actually blows the surrounding gas away, cutting off its own food supply. To reach supermassive sizes in the early universe, a black hole would need to consistently feed at or very near this physical limit for hundreds of millions of years. Some models even suggest it might have needed to briefly exceed this limit in short, violent bursts, a process we call super-Eddington accretion. This is the equivalent of a cosmic athlete performing at the absolute peak of human ability without rest for a lifetime. The quasars we see from 700 million years after the Big Bang are not just anomalies, they are stopwatches. Their brilliant light tells us that the race was already over for some black holes, that they had crossed the billion solar mass finish line while the universe itself was still in its childhood. Every new, distant quasar discovered by telescopes like James Webb tightens the constraints, giving these early giants even less time to form and grow. This forces us to question our most fundamental assumptions. Were the seeds far larger than we thought? Was the early gas supply so dense and plentiful that it allowed for unimaginably efficient feeding? Or is there some aspect of black hole physics in those extreme environments that we simply do not yet understand? The origin of supermassive black holes is not a side mystery. It is a direct challenge to our timeline of cosmic structure, pressing us to find how darkness could organize itself into such profound gravitational anchors almost as soon as the first light began to shine. Scattered throughout the halo of our Milky Way are living fossils. These are the ultra-metal-poor stars, ancient survivors from a time before our galaxy took its modern spiral shape. Their atmospheres are pristine vaults, preserving the chemical makeup of the gas cloud from which they formed over 13 billion years ago. To understand the first stars, we don't just look out into the deep past. We also look inward at these local relics, practicing a science called stellar archaeology. One of the most famous of these relics is a star known as SMSSJ 1300, 36,670,839. Its name is a catalog number, but its story is epic. This star holds the record for the lowest iron content of any star ever measured. Its iron abundance is so low, it's as if you dissolved a single snowflake in an Olympic-sized swimming pool. Yet, intriguingly, it does show enhanced levels of lighter elements like carbon and magnesium. This bizarre chemical fingerprint is the central mystery. How can a star be so poor in iron, a classic product of supernova, yet relatively rich in other elements? The answer points directly to the unique death of a single first-generation star. Astronomers believe this ancient star formed from a cloud polluted by just one population 3 supernova. The specific pattern we see, lots of carbon, almost no iron, suggests that supernova was strangely faint and oddly asymmetric. The leading theory is that the progenitor was a massive first star that collapsed directly into a black hole. In this scenario, most of the heavy iron forged in the star's core would have been swallowed, vanishing forever behind the event horizon. Only the outer layers of the star, enriched with lighter elements like carbon from earlier fusion stages, would have been ejected in a feeble explosion or a strong stellar wind before the final collapse. This would sprinkle the surrounding gas with carbon, oxygen, and magnesium, but leave it almost devoid of iron. That single pollution event then collapsed to form the next generation of stars, including SMSSJ 1300, 36,670,839. 3, locking that chemical story into its atmosphere for us to find billions of years later. Each ultra-metal-poor star tells a different story because each was enriched by a different first star with its own mass and fate. Some show an abundance pattern suggesting a hyper-energetic pair instability supernova, while others hint at more nuanced explosions. By collecting these individual chemical narratives, we are slowly assembling a census of the first stellar generation. We are learning that the first stars were not a monolithic population. They died in a variety of ways, and each death wrote its signature into the next generation. The mystery lies in decoding these signatures with perfect accuracy, separating the signal of that first supernova from any later pollution, and ultimately reading the life story of a star that died before our galaxy even existed, from the atmosphere of a star that still shines today. Those ancient stars are chemical time capsules, but the stage on which they formed was built by an invisible hand. Dark matter did far more than simply provide a gravitational well for gas to collect within. Its fundamental properties we still do not understand, may have directly dictated the character of the universe's first light. The standard model of cosmology relies on what we call cold dark matter. The term cold here means the hypothetical particles move slowly compared to the speed of light. This slowness is crucial because cold dark matter particles are sluggish. They easily clump together under gravity, even on very small scales. This allows tiny density fluctuations in the early universe to rapidly snowball into the first small dark matter halos, the cradles for the first stars. It is the foundation of the bottom-up hierarchical universe we have been discussing. But what if dark matter isn't cold? The alternative is warm dark matter. Imagine particles that are much lighter and faster, zipping through the early cosmos. This slight change in character has a dramatic cosmic consequence. Those fast-moving particles would smooth out the smallest ripples in the density of the early universe. They would wash away the tiniest clumps. In a warm dark matter universe, the first structures to form would be significantly larger. There would be no multitude of tiny halos, only larger, more massive ones appearing later in time. This single shift would profoundly alter the timeline of first light. The first stars would ignite later, and they would likely form in more massive, crowded environments from the start, potentially skipping the era of isolated, monstrous population, 3 stars altogether. The observed pattern of the earliest galaxies, their numbers and their masses, could therefore be a direct test. If James Webb Space Telescope finds a surprising abundance of very small, faint galaxies in the ultra-early universe, it would favor cold dark matter, which readily makes small halos. If it finds fewer small galaxies than expected, and evidence that galaxy formation started a bit later in a more top-down fashion, it could be a tantalizing hint for warm dark matter. But the influence of dark matter might be even more intimate. Some theories propose that dark matter isn't entirely inert. What if certain dark matter particles can interact with themselves or even with ordinary matter in subtle ways beyond gravity? One speculative idea involves dark matter annihilation. In this scenario, when 2 dark matter particles collide within a dense halo, they could annihilate each other, converting their mass directly into energy, into heat. In the cold, pristine gas clouds collapsing to form the first stars, this annihilation energy could provide a potent new source of warming. This extra heat would fight against the molecular hydrogen cooling, potentially delaying collapse, altering the final mass of the star, or even preventing star formation in the smallest halos entirely. Conversely, other models suggest dark matter could aid cooling. If dark matter particles are able to scatter off protons in the gas, they could help carry thermal energy away, making collapse faster and more efficient. We are, in essence, considering whether the invisible majority of matter in the universe was a passive stagehand or an active participant in the drama of first light. Every new observation of the earliest galaxies is thus a double investigation. We are learning about the stars and gas we can see, but we are also conducting a profound experiment on the nature of the dark matter we cannot. The distribution, the brightness, and the very existence of those first flickers in the dark are shaped by the hidden architecture of reality. By mapping the dawn of galaxies, we might finally be reading the first chapter in the instruction manual for dark matter itself, written in the light of the first stars. Buried in the faint whisper of cosmic static is a specific tone, a single note that could become the soundtrack to the universe's awakening. This is the 21-centimeter line, a radio signal emitted by neutral hydrogen atoms. It is a fundamental property of the atom itself, a tiny energy shift as the spin of its electron flips relative to its proton. For the vast clouds of hydrogen that filled the early cosmos, this signal would have been a constant universal hum. Its profound importance to cosmology lies in its journey through time. As the universe expands, the wavelength of this ancient light is stretched. By tuning our radio telescopes to different frequencies, we can listen in to different cosmic epochs. The goal is to map the entire era from the Dark Ages through reionization in 3 dimensions, creating a tomographic image of the young universe as it transitioned from a neutral fog to an ionized clear sky. This would not be a map of galaxies, but a map of the gas itself, revealing the bubbles of ionization blown by the first stars and galaxies as they grew and merged. It would be the ultimate movie of cosmic dawn. Yet, detecting this signal is arguably one of the hardest experiments in all of science. The 21-centimeter signal from the early universe is incredibly faint, a subtle ripple in a sea of radio noise that is billions of times louder. The greatest source of interference is our own celestial neighborhood. The Milky Way galaxy blasts out synchrotron radiation across the radio band, a foreground roar that must be meticulously modeled and subtracted. Then there is the cacophony from human civilization, from television broadcasts to satellite communications, all creating a wall of static that the true cosmic signal must pierce. The technical challenge is like trying to hear a single, specific cricket chirping during a rock concert while standing next to the speakers. The controversy that erupted a few years ago highlights just how difficult this hunt is. A team using a small, ground-based antenna called EDGES reported a detection of an absorption signal in the radio spectrum that was much deeper and broader than any model predicted. If confirmed, it would have been a monumental discovery, the first direct evidence of the cosmic dawn. But the signal's unexpected shape and strength immediately raised eyebrows across the community. Other scientists pointed to potential systematic errors, questioning whether the signal could be contaminated by subtle effects from the instrument itself or from the complex modeling of the galactic foreground. The physics required to explain such a strong signal would have been exotic, suggesting interactions between the primordial hydrogen and dark matter, or a temperature of the early gas that was far colder than anyone thought possible. To this day, the EDGES result remains unconfirmed and hotly debated, a tantalizing but controversial ghost in the data. This is why the next generation of experiments is being built on an epic scale. Projects like the Hydrogen Epoch of Reionization Array, or HERA, and the Future Square Kilometer Array, or SCAR, are not single dishes but vast fields of simple radio antennas spread across remote deserts. Their strategy is to use precise interferometry, combining the signals from thousands of antennas to digitally filter out the foreground noise with unprecedented precision. They are not looking for a single point of light, but for a specific statistical pattern in the radio sky that only the 21-centimeter signal from the early universe can produce. The effort is a global one, a quiet listening post established in some of the most radio-quiet places on Earth, all waiting for the moment when the noise finally parts and the faint, stretched song of the first hydrogen atoms begins to play. Hearing that song would transform our understanding. It would tell us precisely when the first stars switched on, how quickly their ionizing bubbles grew, and whether the process was smooth or violently patchy. It would move us from inferring the dawn from its aftermath to witnessing the event itself, as the first starlight began to interact with the cosmos on the grandest scale. We are waiting, with vast fields of antennas pointed at the sky, for the universe to finally tell us the story of its own birth in its own voice. The faint radio hum of the early universe gives way to a blaze of unexpected light. The James Webb Space Telescope's deepest images were meant to reveal the faint, infant galaxies of the cosmic dawn. Instead, they delivered a shock, scattered across the void at distances corresponding to a time when the universe was a mere 300 to 500 million years old. Webb found galaxies that are not faint infants at all. They are brilliant, massive, and fully formed. There are simply too many of them. This overabundance of bright early galaxies is not just a surprise, it is a direct challenge to our foundational models of how the cosmos builds its structures. According to our best simulations of cosmic evolution, which incorporate dark matter, gravity, and gas physics, the universe should not have had enough time to assemble such large, luminous cities of stars so quickly. It is like opening a history book to the chapter on ancient civilizations and finding skyscrapers. The galaxy's web seas are up to 10 times more massive and 100 times brighter than our models predicted for that epoch. Their starlight suggests they have already converted a vast reservoir of gas into suns at a ferocious, sustained rate. The mystery is profound. How did they get so big so fast? Astronomers are now grappling with three revolutionary and deeply unsettling possibilities. The first is that our understanding of early star formation is fundamentally incomplete. Perhaps in those pristine environments, stars formed with an efficiency we never dreamed possible. Maybe the initial mass function, the rulebook that dictates how many big versus small stars are born, was skewed entirely toward producing brilliant, massive stars in those early galaxies, making them appear disproportionately luminous. Or perhaps stars formed in a continuous, explosive frenzy without the periodic slowdowns we see in later galaxies, allowing them to build up stellar mass at a breakneck pace. The second possibility is even more radical. It forces us to reconsider the invisible scaffolding of the cosmos itself. Could dark matter be different? If dark matter were slightly warm, as we discussed, it would delay the formation of the first small halos. But what if, in certain models, it actually encouraged the rapid growth of the first large halos? Some exotic dark matter candidates could lead to enhanced clustering, creating exceptionally dense knots of gravity that pull in ordinary gas with unprecedented speed, birthing monster galaxies in a single, rapid step. This would mean the blueprint for the universe's structure is written in a language we have not yet deciphered. The third possibility is the most cautious but no less critical. It asks, are we certain about the distances to these galaxies? We measure their redshift, the stretching of their light, to determine how far away and therefore how early in time we are seeing them. But what if some of these galaxies are not as distant as they appear? Could dust within these early systems redden their light, mimicking the signature of a more extreme redshift? While follow-up observations with Webb's spectroscopic instruments are largely confirming the astounding distances, the question of systematic error is always part of the scientific process, a necessary check on a discovery that seems too extraordinary to be true. Each of these paths leads to a different universe. If the star formation models are wrong, we must rethink the entire life cycle of the first stars. If dark matter is the culprit, we are on the verge of one of the greatest discoveries in physics. And if it is a measurement issue, it is a testament to the complexity of interpreting light that has traveled for over 13 billion years. Webb's stunning images have handed us a beautiful crisis. Every bright, early galaxy is a question mark etched in starlight, forcing us to confront the uncomfortable truth that the universe's childhood may have been far more dynamic, powerful, and creatively explosive than our standard stories ever allowed. The boundary between absolute darkness and first light is not a sharp line, but a slow, uncertain dawn. Defining the end of the true dark ages means identifying the moment when the universe ceased to be a featureless expanse of neutral hydrogen and helium and began its journey toward complexity. This transition is the final act of a cosmic prelude, a sequence of subtle events that had to occur before a single star could ignite. The first and most crucial step was the formation of the universe's first molecule. For millions of years, the cosmos was a sea of individual atoms, mostly hydrogen. But to cool down and collapse, that gas needed a way to shed its gravitational energy. That is where molecular hydrogen, or H2, enters the story. It forms when two hydrogen atoms meet and bond on the surface of a rare third particle, usually an electron. This fragile molecule is a remarkably efficient coolant. When it vibrates and rotates after a collision, it emits infrared radiation that can escape into space, carrying heat away from the dense heart of a collapsing gas cloud. Without this molecule, the first stars could never have formed. The creation of H2 was the universe's first chemical reaction, a quiet, invisible process that swept through the dark, setting the stage for everything to come. But what if something else was happening in that profound darkness, something even more exotic? A theoretical possibility exists for objects that could have glowed before nuclear fusion ever began. These are called dark stars. The idea hinges on a speculative but fascinating interaction within dark matter. If certain types of dark matter particles are their own antimatter counterparts, they could annihilate upon collision, converting their mass directly into pure energy, into heat and light. In the dense cores of the first collapsing gas clouds, where dark matter would also be concentrated, this annihilation could provide a powerful, sustained source of energy. A cloud powered in this way would not need nuclear fusion to shine. It would heat up from within, balancing gravity's crush with the outward pressure of dark matter annihilation energy. Such an object could grow to be enormous, up to 1,000,000 times the mass of our Sun, and glow with a soft, diffuse light. It would not be a star as we know it, but a strange, warm balloon of hydrogen and helium, illuminated from the inside by the invisible decay of dark matter. A dark star would be a temporary structure, lasting only as long as its dark matter fuel held out. Once that fuel was exhausted, the cloud would resume its catastrophic collapse, potentially leading to the formation of a monstrously large population, 3-star, or even a direct collapse black hole. The existence of dark stars remains entirely hypothetical, but it represents a breathtaking intersection of particle physics and cosmology. It asks if the very first light we might someday detect from the cosmic dawn could have a shadowy, non-nuclear origin. The precise sequence of events, then, is a delicate chain. First, the universe expands and cools enough for atoms to form, ending the plasma era and beginning the Dark Ages. Then, within the silent dark matter halos, the first molecules of H2 slowly coalesce. This allows the densest knots of gas to begin the slow process of radiative cooling. As they cool, they contract, growing denser and hotter. If dark matter annihilation is possible, this might be the moment a dark star flickers on, delaying the final collapse for a time. If not, the gas continues its inexorable fall inward. At the center of the cloud, a dense core forms a protostar. For a while, it shines only from the heat of its gravitational contraction, growing in mass as more gas rains down upon it. The critical threshold is reached deep in its heart. When the temperature and pressure climb to about 10 million degrees, the protons of hydrogen nuclei overcome their mutual repulsion and begin to fuse into helium. In that instant, nuclear fusion ignites. The outward push of radiation from this new energy source finally halts the gravitational collapse. A stable, self-sustaining star is born. The Dark Ages are over. The timeline of this sequence is what we are desperate to pin down. Did it happen uniformly across the cosmos or in scattered, isolated pockets? Was the transition marked by the soft glow of dark stars, or was it a direct plunge from cold darkness to nuclear fire? Each possibility paints a different portrait of the universe's infancy, from a gentle, warming twilight to a sudden, brilliant flash. Understanding this boundary is to witness the very last moments of the universe's simplicity, before light took permanent hold and the story of everything truly began. The physics of that first collapse seems straightforward, gravity versus heat. But we may have missed a hidden force, one that shapes modern galaxies in profound ways. Magnetic fields are invisible lines of force that thread through the cosmos, guiding charged particles and sculpting the flow of gas. In today's star-forming regions, we see their influence everywhere, from helping clouds shed angular momentum to launching powerful jets from newborn stars. But their origin is a deep cosmic mystery. Did the universe begin with a primordial magnetic field woven into its very fabric, or were these fields born later, forged in the turbulent hearts of the first stars and galaxies? The answer changes everything about how we model the dawn of light. If a significant magnetic field did exist in the early universe, its source is a puzzle in itself. One possibility is that it was created during the violent, inflationary expansion a fraction of a second after the Big Bang, a relic field stretched across the cosmos. Another is that it was generated later by the churning motions of plasma during the epoch of reionization, a cosmic dynamo starting up, but the most intriguing idea connects directly to the first stars. The powerful shockwaves from the very first supernova could have acted like cosmic generators, turning kinetic energy into magnetic energy and seeding the surrounding gas with tangled fields. Each scenario leaves a different imprint, a different starting strength and structure for magnetism in the infant cosmos. Why does this subtle force matter so much for the first stars? In a modern gas cloud, magnetic fields provide crucial support against gravity. They act like a network of rubber bands mixed into the gas, creating pressure and slowing down collapse. They also help transfer angular momentum, allowing a spinning cloud to contract. In the pristine clouds of the early universe, lacking any other support, even a weak primordial field could have been a dominant player. It might have delayed the collapse of the first gas clouds, altering the timeline for the birth of the first stars. It could have influenced how the cloud fragmented, perhaps encouraging the formation of multiple smaller stars instead of a single monolithic giant. The presence of a magnetic field adds a layer of braking and guidance to the raw, unfiltered force of gravity. Later, as the first galaxies assembled, magnetic fields would have taken on an even more dramatic role. They can channel gas flows, funneling material toward the center of a galaxy to feed a growing black hole. They are essential for launching the relativistic jets we see screaming from quasars and active galactic nuclei, beams of energy that can heat intergalactic gas and regulate star formation across entire galaxies. On a galactic scale, magnetic fields help maintain the structure of spiral arms and can even contribute to the stability of galactic disks. Their absence in our models of the early universe is not a minor omission. It is like trying to predict the flow of a river without accounting for the shape of its bed and banks. We are simulating a critical piece of cosmic history with a key ingredient set to zero because we do not know what its initial value should have been. This unknown adds a frustrating but fascinating layer of complexity. When cosmologists run their supercomputer simulations of the first billion years, they must make assumptions. Without knowing the strength and configuration of early magnetic fields, they often run models both with and without them to see how the outcomes differ. The results can be stark. Simulations that include even weak primordial fields show differences in the temperature distribution of gas, the rate at which structures form, and the ultimate masses of the first stars. It becomes another variable in the already difficult task of explaining the surprisingly bright and massive early galaxies seen by James Webb. Could stronger than expected primordial magnetism have helped gas cool and collapse more efficiently, accelerating early galaxy growth? Or could it have provided just enough extra support to prevent the runaway formation of impossibly massive stars, leading to a more populous first generation of suns? We are left with a haunting question. Did the invisible threads of magnetism gently guide the hand of gravity as it wrote the first chapter of the cosmic story? Or did they arrive too late to shape the dawn? The universe's first cities of light were not all brilliant metropolises. According to our best models, the cosmic dawn should have been a time of bustling construction sites, filled with countless faint, small dwarf galaxies. These are the essential building blocks in the hierarchical story of our cosmos, the tiny bricks that merge to form the grand structures we see today. Yet, when we point our most powerful telescopes to the edge of time, we see a sky dominated by surprisingly bright, mature galaxies. The expected swarm of faint dwarfs is conspicuously missing. This is not just an absence, it is a direct challenge to our understanding of how structure grows. Where are all the small galaxies? This mystery cuts to the heart of the cosmic assembly line. In the cold dark matter model, small halos form first. Many of these should have gathered just enough pristine gas to spark a few early stars, becoming faint, diffuse dwarf galaxies. They are the cosmic equivalent of small towns and villages, the necessary precursors to the great cities. Their predicted abundance is not a minor detail, it is a fundamental prediction of our entire cosmological framework. If they are not there, something in our story is profoundly wrong. There are two compelling and very different explanations for their absence. The first is a simple matter of technology. Perhaps these early dwarfs are there, but they are just too faint for even the James Webb Space Telescope to detect. A dwarf galaxy in the early universe might contain only a few million stars, a mere flicker compared to the billions in a bright galaxy. Its light, stretched and dimmed by 13 billion years of cosmic expansion, could be vanishingly faint. We are looking for the faintest possible smudges of infrared light at the very limits of Webb's extraordinary vision. It is possible that with even longer exposure times or future, more powerful telescopes, this predicted population will finally swim into view, confirming the bottom-up model. The search is a painstaking exercise in pushing instrumentation to its absolute breaking point. The second possibility is far more dramatic. What if the small galaxies are missing because they never truly formed? This idea takes us back to the violent nature of the first stars. Imagine one of those early, small dark matter halos. It manages to pull in a cloud of gas, and within it, a single massive population 3-star ignites. Its life is short and its death is catastrophic. The supernova explosion that follows releases an unimaginable amount of energy. In a large halo with strong gravity, this explosion stirs the gas and enriches it. But in a small, fragile halo with weak gravity, the effect is apocalyptic. The blast can blow every last shred of gas clear out of the halo, ejecting it into intergalactic space. The dark matter skeleton remains, but it is now a ghost stripped of its star-forming fuel forever. This process, called feedback, could have sterilized thousands of these small potential galaxies before they ever had a chance to grow. The first stars did not just build the cosmos in this scenario, they also ruthlessly pruned its earliest branches, leaving behind a landscape where only the largest, most resilient halos could survive to become the galaxies we see. The implications of this mystery ripple outward. If faint dwarfs are abundant but unseen, then reionization was likely a gradual process, with millions of small sources slowly eating away at the neutral hydrogen fog. But if feedback truly suppressed them, then reionization was driven by a smaller number of brighter, more massive galaxies, creating larger, more distinct bubbles in the cosmic foam. The pattern of that clearing would look completely different. Finding, or definitively not finding, this population of early dwarfs is therefore about more than just counting galaxies. It is about testing whether the universe's creative and destructive forces were balanced from the very beginning, or if its first light was born from a period of unimaginable stellar violence that shaped everything to come. The search for these faintest sparks continues, a hunt for the missing towns in the universe's first map. The search for those faintest sparks leads us to a different kind of cosmic signal, one of unimaginable violence. Among the most powerful explosions since the Big Bang itself are long-duration gamma-ray bursts. These events, lasting from a few seconds to several minutes, are thought to be the death cries of the most massive stars as they collapse into black holes, firing off narrow, focused beams of energy that can outshine an entire galaxy for a brief, blinding moment. Their incredible luminosity makes them visible across the observable universe, acting as brilliant beacons from the deepest past. This presents a tantalizing possibility. Could the cataclysmic deaths of the very first stars, the population 3 giants, have produced these spectacular gamma-ray bursts? If so, their light, traveling for over 13 billion years, might be reaching our telescopes right now. We could be witnessing the final moments of the universe's first generation of suns in the most dramatic way imaginable. The mystery is whether we have already recorded such an event without understanding its true primordial significance. Identifying a gamma-ray burst from a population 3 star is the ultimate cosmic forensic challenge. The key lies in the afterglow. In the minutes, hours, and days after the initial gamma-ray flash, the explosion interacts with surrounding gas, producing a fading glow across other wavelengths, from X-rays to radio waves. By analyzing this afterglow, astronomers can dissect the chemical makeup of the environment and the nature of the explosion itself. A gamma-ray burst from a first star would leave a very specific signature. Its afterglow would show an almost complete absence of heavy elements. The gas it is expanding into would be pristine, composed only of hydrogen and helium, unlike the metal-enriched surroundings of later stellar deaths. Furthermore, the explosion's energy profile might be unique, reflecting the unusual physics of a star with no initial metals, potentially leading to a jet of unprecedented power or duration. The hunt, however, is filled with obstacles. First, we must catch the burst in the act. Satellites like Swift and Fermi constantly monitor the sky for these fleeting flashes, but pinpointing one that is both extremely distant and has a measurable afterglow is rare. Then we must race to point the world's largest ground-based telescopes at its location within minutes to capture the fading light before it vanishes. Even then, the signal is incredibly faint, and the telltale signs of a primordial environment are subtle lines in a spectrum that is already drowning in noise. There is also the question of timing. Did population 3 stars die in a way conducive to producing a classic long gamma-ray burst? The process requires the star to shed its outer hydrogen envelope, leaving a bare, rapidly spinning core to collapse. Some models suggest the first stars held onto their envelopes tightly, which might lead to a different, perhaps less beamed kind of explosion. Finding even one confirmed first star gamma-ray burst would be a discovery of monumental importance. It would give us a direct, time-stamped measurement of when that specific star died, offering a precise point on the cosmic timeline. The properties of the burst would tell us about the star's mass, its rotation, and the exact mechanics of its catastrophic end. It would be a flashbulb illuminating a single, fleeting scene from the cosmic dawn, freezing a moment of creation and destruction that shaped everything that followed. We are listening for the echoes of the universe's first thunder, hoping that in the brief, brilliant silence after a gamma-ray flash, we might finally hear the story of the very first light going out. The cataclysmic deaths of the first stars did more than just blast space with new elements. They may have forged the universe's first solid particles. In our modern cosmos, tiny grains of dust are everywhere. They are not just cosmic dirt, they are essential building blocks. Dust grains made of silicates and carbon compounds act as microscopic radiators. They help giant gas clouds cool down efficiently, allowing them to fragment into many smaller stars like our Sun. They are also the seeds for planet formation, the raw material of rocky worlds. But in the pristine early universe, there was no dust at all. The mystery is how the first solid flecks of matter condensed out of a gaseous, elemental soup so quickly after the first stars appeared. The leading theory points to the violent end of those massive first stars. In the expanding, cooling debris of a supernova, conditions can become just right for atoms to stick together and form microscopic clusters. Silicon, carbon, and iron atoms, newly forged in the stellar explosion, could nucleate on one another in the chaotic outflow, growing into the first soot-like grains. Another possibility is that dust formed not in a sudden blast, but in the slower, dense winds blowing from the surfaces of aging giant stars before they exploded. Each method would produce a different kind of dust with different sizes and compositions. The puzzle is one of speed and scale. To explain the dusty galaxies we are now seeing, dust production in those first stellar deaths had to be astonishingly efficient. A single supernova might have needed to convert a significant fraction of its heavy elements into solid dust almost immediately. This is where the James Webb Space Telescope delivers another stunning surprise. Webb's infrared vision is perfectly suited to detecting the warm glow of dust, and it has found it in galaxies observed when the universe was less than 700 million years old. These are galaxies that, in cosmic terms, are only toddlers, For them to be so dusty, the first generation of stars must have lived, died, and processed their debris into solid form within just a few 100 million years. That is an incredibly tight timeline. It suggests the first supernova were not just element factories, they were prolific dust mills operating with a speed and efficiency we rarely see in the nearby universe. Perhaps the unique conditions of a pair instability supernova, with its immense energy and particular mix of elements, created a perfect environment for rapid dust condensation. Or maybe we have underestimated the role of those slower stellar winds, which could have begun sprinkling dust into space even before the final explosion. The presence of this early dust forces a profound rethink. It means the universe did not stay pristine for long. Almost as soon as the first heavy elements existed, they began clumping into solids, changing the very rules of physics for the next generation of star formation. Gas clouds enriched with this dust could cool and fragment more easily, potentially leading to a rapid shift from isolated monster stars to populous clusters of smaller suns. The cosmic dawn, therefore, may have had a brief, gritty phase where the first starlight began to glint off trillions of freshly made microscopic particles. This dust was the universe's first step toward building something solid, the quiet, gritty foundation for all the rocky planets and ultimately the ground beneath our feet. How something so small could appear so quickly after the first light is a mystery written in infrared, waiting for its final grain of truth. That first dust was more than a building block, it was a tracer, revealing the hidden architecture on the grandest scale. The universe is not a random scattering of galaxies. It is a vast, intricate network, a cosmic web of dense filaments and immense, empty voids. This structure is woven by the gravitational pull of dark matter, an invisible skeleton that has shaped everything from the beginning. The profound mystery is how the first stars and galaxies mapped onto this hidden framework. Did they ignite like fairy lights along the densest dark matter filaments first, tracing the web's main arteries? Or did they appear in a more chaotic pattern, lighting up isolated knots before the connections were fully drawn? To answer this, astronomers act as cosmic cartographers using a technique called tomography. Just as a medical CT scan builds a three-dimensional image of the human body from many X-ray slices, cosmic tomography builds a map of the early universe from many lines of sight. They combine two powerful tools. First, they pinpoint the three-dimensional locations of the earliest galaxies using their redshift, placing each one as a point of light in the vastness of time. Second, they use the Lyman alpha forest, the absorption lines in quasar spectra, to map the diffuse hydrogen gas that fills the space between those galaxies. This gas is not random. It clumps along the same dark matter filaments that attract the galaxies themselves. By stacking thousands of quasar sightlines and galaxy positions, a breathtaking picture begins to emerge. We can start to reconstruct the skeleton of the young cosmos, seeing where the gas is thick and where it is thin, and how the islands of early starlight relate to that underlying geography. The ultimate test is to hold this observed map up against the universe predicted by our best supercomputer simulations. These simulations, which model the evolution of dark matter and gas over billions of years, generate their own cosmic webs. The question is, do they match? Do the simulated filaments have the same thickness and distribution? Do galaxies in the simulation light up in the same places with the same clustering pattern as the real galaxies we observe with telescopes like James Webb? Even the tiniest discrepancy here is not a minor error, it is a potential clue to new physics. If the observed web is more developed, with brighter galaxies clustered more tightly along filaments than the simulations predict, it could mean that dark matter is clumpier, or that gas cooled and collapsed into stars more efficiently than our models allow. It could hint that gravity behaved slightly differently on those immense scales, or that some unknown process helped structure the universe faster than we thought possible. Mapping the first large-scale structure is like finding the faded outline of the universe's blueprints. Every filament traced by an early galaxy, every void that remains stubbornly dark, is a data point in a cosmic equation. By comparing the real, observed blueprint to the simulated one, we are conducting a fundamental audit of our entire understanding of cosmic evolution. The goal is to see if the dark matter skeleton we infer truly fits the body of light that grew upon it, or if, in the deepest past, the universe followed a set of rules we have yet to fully read. The intricate web of dark matter set the stage, but the actual growth of the first cosmic giants happened on a much smaller, more violent scale. Around a newborn star or a fledgling black hole, gravity pulls in a swirling vortex of gas. This spiraling maelstrom is called an accretion disk, and it is the engine of growth for every massive object in the universe. For the first stars and black holes, these disks were forged in a unique and extreme environment. Without a single grain of dust or a trace of heavier elements, they operated under a completely different set of physical rules. This creates a pivotal and often overlooked mystery: the stability of the first accretion disks. In our modern universe, accretion disks around young stars or black holes are efficient radiators. Dust grains and complex molecules like carbon monoxide within the gas act as a coolant, allowing the disk to shed heat as infrared light. This cooling keeps the disk relatively thin and stable, enabling material to spiral inward smoothly over time. But in the primordial disks feeding the first objects, there was no dust, no metals. The only coolant available was molecular hydrogen. While hydrogen can cool the gas, it is vastly less efficient than the metallic coolants we have today. The result would have been a disk that struggled to radiate away its immense gravitational energy. As gas particles collided and rubbed together in the furious spiral, they would have heated up to staggering temperatures, perhaps millions of degrees. A hotter disk is a puffier disk, one that is swollen and thick with turbulent, searing gas. This changes everything about its behavior. The critical question is whether these thick, superheated disks could hold themselves together. The immense heat creates pressure that fights gravity's pull, potentially stabilizing the disk, but there is a tipping point. If the disk becomes too hot and thick, it might cross a threshold where its own gravity becomes strong enough to cause local clumps within the disk itself. In other words, the disk could start to fragment, collapsing in on itself to form secondary stars or even smaller black holes right there in the swirling chaos. This is not a minor detail, it is a fundamental control mechanism for growth. A stable, smooth disk acts like a well-organized conveyor belt, delivering gas steadily to the central object, allowing for rapid, continuous growth. A disk that fragments is a messy, inefficient factory. The formation of new objects within the disk would interrupt the smooth flow of material, siphoning off fuel and potentially ejecting gas entirely through gravitational interactions. The central star or black hole would find its meal repeatedly interrupted, its growth stuttering and slow. This micro-physical detail has macro consequences, especially for the race to build the first supermassive black holes. If the disks around the first black hole seeds were prone to fragmentation, it would have placed a severe speed limit on their growth. They could not have consistently fed at the maximum rate, making it even harder to explain how we see billion solar mass quasars so early in cosmic time. Conversely, if the disks remained stable despite the heat, it means the conveyor belt was wide open, allowing those seeds to gorge on the pristine gas and balloon in size with terrifying speed. We cannot see these ancient disks directly, but their theoretical properties are a crucial variable in every simulation of early structure formation. By modeling the complex physics of radiation, hydrodynamics, and gravity in a metal-free environment, scientists are trying to determine which outcome was more likely. The stability of the first accretion disks is a silent, invisible drama that played out at the feet of the universe's first giants. a hidden struggle between heat and gravity that may have decided how quickly the cosmos could build its most monstrous inhabitants. Our picture of a solitary giant star collapsing in isolation may be incomplete. The first stars might not have been lonely titans. Many could have been born with companions, locked in a gravitational dance from their very first moments. This possibility, the existence of primordial binary star systems, unravels much of what we think we know about the cosmic dawn. In our modern universe, most massive stars are found in binary or multiple systems. It is the rule, not the exception, so why would the first generation be any different? The challenge is that our simulations of primordial cloud collapse give conflicting answers. Some models, focusing on the slow, monolithic collapse of pristine gas, suggest single stars are the most likely outcome. Others, which account for more turbulent conditions and the possibility of disk fragmentation around a growing protostar, show that the infalling gas can easily break into 2 or 3 distinct clumps, birthing sibling stars. If binaries were common, everything changes. The life and death of a massive star is profoundly altered by a close companion. Instead of a straightforward collapse, a star could have its outer layers stripped away by its partner's gravity. This can expose its hot, helium-rich core prematurely, changing the type of supernova it produces. In a tight binary, one star might collapse into a black hole that then begins to siphon material from its still living companion. This would create the first X-ray binary, a system flooding its surroundings not with gentle starlight, but with piercing, high-energy X-ray radiation. This is a different kind of ionizing force altogether. X-rays are far more penetrating than ultraviolet light. They could travel much deeper into thick clouds of neutral hydrogen, potentially ionizing vast, distant regions of the early cosmos in a way that ultraviolet photons from stars alone could not. The presence of many such systems could have made reionization a more efficient and uniform process, or perhaps a more chaotic one, with high-energy bubbles appearing in unexpected places. The chemical legacy would also be transformed. The transfer of mass between stars in a binary system creates exotic nuclear reactions, producing unique isotopes. The supernova explosion in a binary might be triggered or altered by the presence of its partner, ejecting a different mix of elements into space. The hunt for the chemical fingerprints of the first stars in ancient, metal-poor stars becomes even more complex, as we must now look for signatures not just of single-star deaths, but of intricate stellar dances and mergers. This mystery forces us to reconsider the foundational environment of the first light. Was the early universe illuminated by isolated beacons, or was it flickering with the complex, interacting fires of the first stellar families? The answer lies in the faint, blended light of the most distant galaxies, and in the precise chemical codes locked within our galaxy's oldest stars, waiting to tell us if the first chapter of cosmic history was a solo performance or a duet written in fire. The brilliant galaxies we see at the edge of time are not just discoveries, they are data points in a cosmic census. But any census has a fundamental flaw: you can only count what is in your survey area. Our most powerful telescopes, like the James Webb Space Telescope, peer into the deep universe through a method known as the deep field. They stare at a single, seemingly empty patch of sky for hundreds of hours, collecting the faintest photons from the most distant objects. The result is a breathtaking image, a core sample drilled 13 billion years into the past. But this method presents a profound and unsettling statistical problem. We are looking through a keyhole. That keyhole might be only a few arcminutes across on the sky, a patch of darkness smaller than a grain of sand held at arm's length. The mystery is whether this tiny window offers a fair, representative view of the entire infant universe, or if we are simply peering into an exceptionally bright and crowded cosmic neighborhood. This uncertainty has a formal name: cosmic variance. It is the idea that the universe, especially on large scales, is not perfectly smooth, matter clumps. If your telescope's field of view is too small, you might accidentally point it at a dense cluster of early galaxies, or you might point it at a vast, empty void. The conclusions you draw from those two images would be radically different. One would suggest a universe teeming with bright, early galaxies, the other a universe where galaxy formation was slow and hesitant. This is not a hypothetical concern. It directly impacts the most shocking discoveries from the James Webb Space Telescope. When Webb sees an abundance of surprisingly bright and massive galaxies in its early deep fields, we must ask a critical question. Are we seeing a universal truth about the early cosmos, or have we simply won the cosmic lottery and pointed our telescope at the ancient equivalent of a downtown metropolis? The uncertainty introduced by cosmic variance makes it incredibly difficult to draw definitive global conclusions. We cannot say with absolute certainty that galaxy formation was universally efficient or fast, only that it was efficient and fast in this particular patch of sky we happen to study. To combat this, astronomers must become cosmic surveyors. The solution is to take more samples to stare through many different keyholes scattered across the sky. Each new deep field is like taking a core sample from a different part of the ancient forest. By comparing them, we can begin to map the patchiness of the early universe. If every deep field shows a similar abundance of bright galaxies, then cosmic variance is low, and we are likely seeing a true, universal characteristic of that epoch. But if some fields are crowded and others are sparse, then the variance is high, and our single, early images may have been misleadingly rich. This statistical challenge touches every major mystery. It affects our estimates for the timeline of reionization, as one field might show a region already cleared of neutral hydrogen while another shows persistent fog. It skews our measurements of the early growth of supermassive black holes, as a cluster of galaxies might foster more rapid black hole feeding through mergers and interactions. It even influences our search for the first stars, as their chemical fingerprints might be more common in some regions than others. We are, in a very real sense, trying to understand the entire history of the cosmos by examining a handful of fossil fragments, never knowing for sure if the fragments we have are typical or extraordinary. Every new deep field observation is a step toward a fairer sample, a move from a captivating anecdote to a reliable statistic. The grand puzzle is not just what we see in the darkness, but whether the darkness itself is hiding a deeper pattern we have yet to fully glimpse. The pristine gas of the early universe was not a still, silent pool. It was a roiling, chaotic sea. Turbulence, the violent and disordered motion of fluids, is a powerful force in modern star-forming clouds, and it almost certainly played a role in the first ones as well. But this presents a deep mystery. In today's clouds, turbulence is constantly stirred up by external events. The shock waves from nearby supernova explosions slam into gas clouds, compressing them and triggering whirlpools of motion. The powerful winds from massive stars can carve out bubbles and send ripples through the interstellar medium. Even the gentle gravitational tides from passing galaxies can stir the pot. Yet in the primordial universe, before the first stars lived and died, none of these drivers existed. The cosmos was a blank slate, so where did the turbulence come from? The answer must lie in the birth of the cosmos itself. One powerful source was likely the gravitational growth of structure. As dark matter halos formed and merged, they didn't do so smoothly. These collisions and interactions would have set the ordinary gas within them into a churning, violent motion. Imagine two streams of water colliding in a river, creating whirlpools and eddies. On a cosmic scale, the merging of two gaseous halos would have been an immensely energetic event, injecting tremendous turbulence into the combined system. Another fascinating possibility involves a slight mismatch between dark matter and ordinary matter. In the very early universe, dark matter and gas are thought to have moved together. But as structures grew, subtle differences might have emerged. The dark matter, interacting only through gravity, could form clumps faster. The gas, feeling pressure and able to radiate heat, might lag slightly behind. This could create a situation where the gas is effectively streaming through the stationary dark matter wells, and that streaming motion would naturally generate turbulence, like wind creating waves on the ocean. The level of this early chaos is not a minor detail, it is a critical control knob for the first stars. Turbulence has a dual, almost contradictory nature. On one hand, it can promote star formation. When turbulent motions collide, they create dense, high-pressure regions, knots within the cloud where gravity can get a stronger grip. These knots can become the seeds for protostars. In this way, turbulence acts as a sculptor, carving the diffuse gas into denser lumps ripe for collapse. On the other hand, turbulence also provides support. The chaotic, supersonic motions create a kind of pressure that pushes outward, resisting the inward pull of gravity. A highly turbulent cloud might take much longer to collapse, or it might fragment into many smaller pieces instead of a single massive one. The final outcome hinges on a delicate balance. Was the turbulence in the first cloud strong enough to create dense seeds, but not so strong that it entirely held off collapse? Or was it weak, allowing for a more monolithic, quiet condensation of gas into a solitary giant? Our most advanced simulations are now trying to incorporate this crucial ingredient. They model not just gravity and cooling, but the complex fluid dynamics of supersonic turbulence in a metal-free gas. The results show that even a moderate amount of turbulence can drastically change the story. It can lead to a wider variety of stellar masses from the very beginning, potentially producing not just monstrous stars, but also a population of more modest-sized ones alongside them. This would mean the first stellar generation was more diverse than we once imagined. The faint, ancient starlight we hope to detect and the chemical patterns we find in the oldest stars are all echoes of that first cosmic chaos. The turbulence in the primordial gas was the universe's first stirring, a violent cradle that rocked the first stars into being, and its forgotten rhythms are still written into the family tree of every galaxy. Their lives were measured in cosmic moments, not eons. A star like our Sun will burn steadily for 10 billion years, a patient, enduring beacon. But the first stars, the population 3 giants, lived on a different scale entirely. With masses hundreds of times greater, they were cosmic infernos burning their nuclear fuel at a frantic, desperate rate. Their entire existence, from ignition to catastrophic death, might have spanned only 2 or 3 million years. To put that in perspective, if the Sun's lifespan were a full 24-hour day, a massive population 3 star would blaze across the sky and vanish in less than 2 minutes. This breathtaking brevity is the key to understanding their true power. Their influence was not in their endurance, but in the ferocious intensity of their brief presence. They were not gentle lights in the dark, they were violent sculptors, and the tools they used are called feedback. This is the collective term for the ways a star interacts with and alters its own environment. For these first stars, feedback was not a side effect, it was their primary legacy, a force that dictated the future of their cosmic neighborhood. The first form of feedback was their light itself. From the moment they ignited, they flooded their surroundings with an intense bath of ultraviolet radiation. This harsh light began ionizing the nearby hydrogen gas, stripping electrons from atoms and heating the region. But more than just light, these massive stars also unleashed powerful stellar winds. The incredible radiation pressure at their surfaces literally blew their own outer layers away in a continuous supersonic gale, a hurricane of hydrogen and helium streaming into space. These winds carved out vast cavities in the primordial gas, clearing the area around the star. Then came the final, definitive act of feedback, the supernova. Whether it was a pair instability event that completely obliterated the star or a core collapse that left a remnant, the explosion was an apocalypse. It injected an unimaginable amount of kinetic energy, heat, and newly forged heavy elements into the surrounding void. The combined effect of these processes, the radiation, the winds, the explosion, created a powerful shockwave that raced outward through the interstellar medium. This is where the mystery of quantification becomes critical. We can model these forces, but we do not know their precise strength. How much gas did the stellar winds actually push away? How large was the ionized bubble around each star? Most importantly, how far did the supernova shockwave travel, and how thoroughly did it mix the first heavy elements into the pristine gas? The answers determine whether a star's feedback was a creative or destructive force on a local scale. In many scenarios, the feedback was so overwhelmingly powerful that it was destructive first. The shockwave would have heated the nearby gas to millions of degrees, making it so hot and turbulent that it could not collapse under its own gravity for millions of years. The stellar winds would have swept the area clean of star-forming fuel. In essence, a single massive star could have sterilized its entire host dark matter halo, and perhaps even neighboring halos, preventing any new stars from forming in that region for a long, quiet time. The first star would literally snuff out the possibility of immediate siblings. This creates a fascinating stop-start rhythm for the early universe. A region would darken as a gas cloud collapsed. Then, a brilliant star would flash into existence, flooding the area with light and wind. A few million years later, a supernova would blast it clean. Then, silence. The hot, enriched gas would need to slowly cool, radiate its energy, and fall back into the gravitational wells of dark matter, perhaps over tens or even hundreds of millions of years, before the cycle could begin again and a second generation of stars could form. This feedback loop set the tempo for early galaxy growth. A galaxy that hosted many massive first stars might have its star formation violently suppressed for a long period, stunting its early growth. A galaxy where the first stars were slightly less massive, or where the gas distribution was more resilient, might recover faster and build stellar mass more quickly. The chemical enrichment was equally controlled by feedback. A supernova that exploded in a low-density environment would blast its elements far and wide, creating a thin, uniform sprinkle of metals. One that exploded into a dense, gas-rich region would enrich a smaller area much more heavily, creating a potent chemical hotspot for the next stellar generation. So the specific rhythm of flashes and silences, the precise strength of each stellar outburst, wrote the rulebook for how quickly galaxies could assemble and how chemically diverse they would become. We are listening for that rhythm in the fossil record. The ages and chemical compositions of the oldest stars in our galactic halo are not random. They are a cadence, a pattern of bursts of star formation separated by pauses, all orchestrated by the feedback of the very first short-lived giants. Their brief, brilliant lives were the metronome that set the beat for the cosmic dawn. The brief, violent rhythm of the first stars left behind a silent population of black holes. Today, we are learning to listen for their collisions. When two of these ancient remnants spiral together and merge, they shake the very fabric of space-time, sending out ripples called gravitational waves. Our observatories on Earth, like LIGO and Virgo, have now detected dozens of these cosmic tremors, opening a completely new window on the universe. But within this growing catalogue of mergers lies a profound mystery. Could some of these events be the final, crashing dance of black holes forged from the very first generation of stars? Distinguishing a primordial merger from a more recent one is the ultimate cosmic detective challenge, and it all comes down to the masses and spins of the black holes involved. In the modern universe, black holes are born from the deaths of stars rich in heavy elements. This environment leads to a wide variety of outcomes, producing black holes that might range from about 5 to perhaps 50 times the mass of our Sun. But the first stars were different. Formed from pure hydrogen and helium, they likely grew to staggering sizes. If they collapsed directly into black holes, those primordial seeds could have been significantly heavier from the start, perhaps between 50 and several hundred solar masses. So, if our gravitational wave detectors pick up a signal from two black holes merging, and each one is, say, 80 times the mass of the Sun, that immediately raises eyebrows. Black holes that large are difficult to explain through the death of modern, metal-rich stars. They are, however, perfectly consistent with the predicted mass range of the first stellar generation. The spin of the black holes offers another clue. In a typical stellar binary born today, the two stars have a long, shared history. They often spin in alignment with each other and with the orbit of their system. When they collapse and merge, that alignment can be preserved, leaving a signature in the gravitational wave signal. But the first black holes might have a wilder origin story. They could have formed in isolation and only been brought together much later by the chaotic dynamics within a dense star cluster. In that scenario, their spins would be randomly oriented, bearing no relationship to their orbital motion. A gravitational wave signal showing such misaligned, chaotic spins would be a tantalizing hint of a primordial pairing. The search is not just for one odd event, but for a population. If we begin to see a cluster of mergers where the black hole masses are curiously similar and all within that high, pristine mass range, it would be strong statistical evidence that we are witnessing the final acts of the population 3 era. This is where future observatories, especially the space-based detector called LISA, will change everything. LISA will be sensitive to a lower frequency of gravitational waves, allowing it to detect the mergers of much more massive black holes, including those in the supermassive range from the earliest quasars. It could hear the gentle, years-long in-spiral of black holes that formed in the universe's first dense star clusters, providing a clean, undisturbed signal. Finding even one confirmed primordial black hole merger would be a discovery of staggering importance. It would give us a direct physical measurement of the masses of the first stars, confirming or refuting our most fundamental theories about their formation. It would provide a timestamp for when those stars lived and died, adding a precise day to point to our cosmic timeline. Most profoundly, it would mean we are no longer just inferring the properties of the first stars from their chemical pollution or their faint, distant light. We would be feeling the literal vibrations from their final, catastrophic moments, sensing the aftershocks of events that occurred over 13 billion years ago. We are now listening to the universe with ears made of laser light and mirrors, waiting for the day it whispers to us in the language of gravity, telling the story of its very first darkness collapsing in on itself. That violent heating of the cosmos left a thermal record in the gas itself. We can read this ancient thermometer by studying the same Lyman alpha forest that maps the universe's structure. The width of those dark absorption lines in a quasar's spectrum doesn't just tell us where the hydrogen is, it tells us how fast the atoms are moving. In a hot gas, atoms zip around at high speeds, broadening the absorption lines. In a cold gas, they move more slowly, creating sharper, narrower lines. By carefully measuring this subtle broadening, astronomers can estimate the temperature of the intergalactic gas at different cosmic epochs, essentially taking the universe's temperature billions of years ago. The results are puzzling. The gas, as expected, heats up during reionization. That blast of ultraviolet light from the first stars and galaxies pumps energy into it. But later, when the universe is about 1 to 3 billion years old, measurements suggest the intergalactic medium is cooler than our best models predict. It's as if we opened an oven, felt a blast of heat, but then found the interior cooling down faster than the insulation should allow. This thermal mystery forces us to question what was heating the gas and, more importantly, what was cooling it so effectively. The primary suspect for the unexpected cooling is an omnipresent cosmic fixture, the cosmic microwave background. This afterglow of the Big Bang fills all of space, and it has a temperature that drops steadily as the universe expands. In the early cosmos, this background radiation was much warmer than it is today. The hydrogen gas in the universe, after being heated by starlight, would naturally try to cool down by radiating its own energy away. But here's the catch: it can only cool if its temperature is higher than that of the cosmic microwave background surrounding it. If the two temperatures are equal, there's no net energy flow and cooling stops. Think of it like a hot cup of coffee in a warm room. It cools until it reaches room temperature, then it stops. Our models assumed the cosmic microwave background set this universal floor, a minimum temperature the gas couldn't fall below. Yet the measurements hint the gas may have dipped even cooler. How is that possible? Either our temperature measurements are subtly off, or something was helping the gas shed extra heat, acting like a cosmic refrigeration unit that worked below the ambient temperature. One speculative idea involves a different kind of interaction. Could the hydrogen gas have been cooled through interactions with something else entirely, like a stream of cold, dark matter particles? Or perhaps the heating sources themselves were less efficient than we think. Maybe the first galaxies were less effective at pumping high-energy radiation into the vast voids between them, leaving large regions of gas to cool more peacefully and thoroughly. Alternatively, the distribution of the heating might have been incredibly patchy, with most of the energy focused in dense regions near galaxies, while the vast intergalactic wilderness remained in a cooler, more pristine state. This isn't just a minor discrepancy in a data table. The temperature of the early universe is a critical dial in the machine of structure formation. Warm gas is puffy and resistant to collapse. It takes more gravity to pull it into a new galaxy. Colder gas is denser, more compliant, and ready to fragment into stars. If the gas was systematically cooler than we thought, it means the conditions for forming the second and third generations of galaxies were even more favorable, potentially explaining how cosmic structure assembled with such astonishing speed. The thermal state of the cosmic dawn is a forgotten variable, a background hum that set the efficiency of everything that followed. By trying to understand why the ancient universe seems to have run a little too cool, we might be uncovering a subtle new law of cosmic thermodynamics, or finding a ghostly interaction between the world we see and the dark reality that shapes it. Scattered around our galaxy like ancient, glittering beacons are the globular clusters. These are dense spheres of up to 1 million stars, all bound together by gravity in a volume so tight that the core would be a sky ablaze with neighboring suns. Many of these clusters are among the oldest objects we can identify, with stars nearly as ancient as the universe itself. Their chemical makeup tells a clear story. They are incredibly metal-poor. This means they formed from gas that was only lightly enriched by the very first generations of supernova. These are not just relics, they are time capsules from the era we have been exploring, and they hold a pivotal mystery. Did these immense star clusters form as the universe's very first independent structures, or were they born within the first fragile dwarf galaxies? The answer rewrites the early sequence of cosmic architecture. To understand the puzzle, picture the environment of the cosmic dawn. We have discussed the first massive stars exploding, heating their surroundings and seeding the gas with the first heavy elements. In this turbulent, energized landscape, vast clouds of this slightly enriched gas would have been collapsing under their own gravity. The question is one of scale and isolation. One possibility is that a particularly massive and dense cloud of this early gas collapsed directly, not into a loose, sprawling dwarf galaxy, but into a single, incredibly dense and coherent star cluster. In this scenario, a globular cluster could have been the first gravitationally bound structure to switch on its lights, a brilliant, isolated island of stars shining in the dark long before the galaxy that would eventually host it even existed. It would be a primordial city-state born whole from the chaos. The alternative is that globular clusters are the dense, surviving cores of the first dwarf galaxies. Imagine one of those early, small galaxies forming, At its heart, where the gas is densest, a burst of frantic star formation creates a tight knot of stars. Over billions of years, the weaker outer regions of this dwarf galaxy are stripped away by tidal forces as it orbits our larger Milky Way. What remains is the resilient, dense core, the globular cluster we see today. In this story, the cluster is not a pioneer but a survivor, the indestructible heart of a galaxy that was otherwise consumed. How do we distinguish between these two origins? Astronomers act as cosmic historians, using three main lines of evidence. First, they measure ages with exquisite precision. By locating the point on the Hertzsprung-Russell diagram where stars begin to turn off the main sequence, they can date the entire population. For many globular clusters, that age is indeed staggering, often over 12.5 billion years. They were born when the universe was in its wild youth. Second, they decode chemical compositions. Not only are these clusters metal-poor overall, but they often show a fascinating internal consistency. All the stars within a single cluster tend to have very similar amounts of elements like iron. However, they can show surprising variations in lighter elements like oxygen, sodium, and aluminum. This pattern suggests the cluster formed from a gas cloud that was enriched by a very specific, localized set of supernovae, and then quickly turned that gas into stars before more explosions could pollute it further. This favors a rapid, monolithic collapse, whether as an independent structure or as the intense nucleus of a small galaxy. The third clue comes from dynamics, the motion of stars within the cluster. Some of the oldest globular clusters show signs of having been born with virtually no dark matter. This is a crucial detail. If they formed as the cores of dwarf galaxies, they should still retain a halo of dark matter, the same invisible scaffolding that holds all galaxies together. The apparent lack of it suggests they may have formed in a different way, perhaps from a cloud of ordinary gas that collapsed without a significant dark matter component to begin with. Each new observation tightens the narrative. The James Webb Space Telescope, by studying the earliest stages of galaxy formation, is looking for the infant versions of these clusters. Are there incredibly bright, compact knots of stars within the first galaxies that could be newborn globular clusters? Or do we see isolated, ultra-compact stellar systems floating in the void, potential pioneers of structure? The ancient clusters orbiting our Milky Way are the end product of that era. Their present-day dynamics and chemistry a complex code we are still learning to crack. Whether they were the universe's first independent cities or the fortified keeps of its first fallen kingdoms, their silent, ancient light holds the secret to how the cosmos first learned to build in concentrated, enduring form. The remnants of those first cataclysms did not remain where they were born. A black hole or neutron star, the dense corpse of a first-generation giant, is an object of immense gravity. In the bustling stellar environment of a young proto-galaxy, such a heavy object does not stay put. It begins a slow, inevitable drift toward the center of the gravitational well it inhabits, a process called dynamical friction. Imagine a bowling ball rolling through a room filled with ping-pong balls. As it moves, it gravitationally tugs on the lighter balls, scattering them. With each interaction, the bowling ball loses a tiny bit of momentum, slowing down. In cosmic terms, the black hole is the bowling ball, and the surrounding stars and dark matter are the ping-pong balls. Over hundreds of millions of years, this gentle but persistent braking action causes the remnant to sink, spiraling inward toward the very heart of its host dark matter halo. This journey sets the stage for the next act in the mystery. What happens when these ancient travelers reach the center? They find company. Other black holes and neutron stars, the remnants of other first stars from the same region, have made the same pilgrimage. In the dense, chaotic core of the young structure, these objects can pair up, forming binary systems through gravitational capture. Once locked in a dance, they gradually lose energy by emitting gravitational waves, spiraling closer and closer until they finally merge in a violent collision that shakes the fabric of space-time. Each merger creates a new, more massive black hole. This process, repeated over eons, is like a cosmic game of consolidation, where small grave sites of stellar mass combine to form larger and larger gravitational anchors. But there is an even more profound possibility. Could one of these growing remnants, born from the very first stellar collapse, have become the seed for the supermassive black holes we see powering brilliant quasars when the universe was still young? It is a tantalizing chain of events. A first-generation black hole of a few hundred solar masses sinks to the center of its halo. There, it finds a rich reservoir of pristine gas, perhaps funneled in by the same dynamical processes. It begins to feed, growing steadily. It merges with other stellar remnants that have sunk to the center. With each merger and each meal, it grows larger and its gravitational pull becomes stronger, allowing it to pull in gas even faster. This cycle could, in principle, bootstrap a stellar mass seed into a supermassive monster within a few 100 million years. The race against time to explain early quasars might have been won by these persistent central accumulators. Yet the journey is not always one of orderly growth and central aggregation. The universe is a violent place, and these remnants can be violently exiled. When two black holes merge, the event is not perfectly symmetrical. The emission of gravitational waves can kick the newly formed black hole in a specific direction, like the recoil from a gun. If this gravitational wave kick is powerful enough, it can eject the black hole entirely from its host galaxy, sending it flying into the intergalactic void at speeds of thousands of kilometers per second. There it becomes a rogue black hole, a dark wanderer traveling through the emptiness between galaxies, possibly accompanied by a faint halo of captured stars. Other remnants might be ejected through complex gravitational slingshot interactions in a crowded galactic core, where a close encounter with multiple objects can fling one out into the darkness. This creates a hidden population of isolated black holes and neutron stars adrift in the vast cosmic ocean, completely dark and nearly impossible to find. Their existence is predicted, but their numbers and distribution are pure speculation. They are the ghosts of the first stars cast out from the cities they helped build. Tracing the ultimate fate of any single first stellar remnant is therefore an exercise in cosmic probability. We must follow countless potential paths through a labyrinth of gravitational interactions, merger events, and accretion episodes across 13 billion years. Did the core of a specific population 3-star end up as part of the supermassive black hole at the center of a galaxy like our Milky Way? Was it ejected long ago and now drifts alone in the abyss? Or is it still orbiting in the galactic halo, a silent witness to the dawn of time? Each path represents a different thread in the tapestry of cosmic history. The chemical elements that star created are now part of new stars, planets, and perhaps living beings. But its gravitational shadow, the remnant of its collapse, has its own epic story of migration, consolidation, and sometimes exile. The first stars shone briefly, but their dark hearts may still be with us, hidden in the centers of galaxies or lost in the deep dark, carrying the imprint of the universe's first moments into the far future. Their final resting places are maps to the gravitational history of the cosmos itself, charts we are only beginning to decode. The universe began with a simple, perfect symmetry. Hydrogen, helium, and the silent pull of dark matter were its only ingredients, its only laws. For hundreds of millions of years, it was a place of profound simplicity, a vast, uniform expanse where nothing changed and nothing complex could ever happen. Then the first stars switched on. In that moment, the universe crossed a threshold. It was no longer just a container of simple elements, it became a forge. The nuclear fires within those stars began the alchemy of creation, fusing hydrogen and helium into carbon, oxygen, nitrogen, and iron. Their explosive death scattered these new elements like seeds, polluting the pristine void with the raw materials for everything to come. Rocks, oceans, organic molecules, and ultimately living, thinking beings all were made possible by that first, irreversible step away from simplicity. This leads us to the final and perhaps most profound mystery of all. Does this undeniable arc from simplicity to complexity imply a kind of cosmic evolution, a built-in direction to the story of the universe? It is a question that sits at the boundary between science and philosophy. In a strict biological sense, evolution requires reproduction, mutation, and selection. The cosmos does not reproduce itself. Yet, when we look at the 13 billion-year narrative from quark to quasar, from molecule to mind, we see an undeniable trend. The universe has grown more structured, more diverse, and more complex over time. The first stars broke the symmetry of the dark ages. Gravity pulled them together into galaxies, which then built even more stars enriched with heavier elements. Those elements allowed for the formation of planets, and on at least one of those planets, chemistry became intricate enough to spark life, which then evolved consciousness. This is not a random walk, it is a cascade where each new level of complexity creates the conditions for the next. The universe seems to have a latent potential for building intricate structures, a potential that was unlocked quite literally by the first light. This brings us to the most startling part of the story, our own place within it. We are not separate observers looking at a distant cosmic stage. We are a product of that stage, written into the script from the very first act. Every atom of oxygen in the air we breathe, every particle of iron in our blood, every atom of carbon that forms the foundation of our DNA was forged in the heart of a star that lived and died long before our sun was born. We are not just made of stardust, we are the universe in a very real sense, becoming aware of itself. The hydrogen that fused in the first stars is now part of the neural circuitry that allows you to wonder about them. This is a closed loop of astonishing beauty. The universe created the conditions for complexity. Complexity eventually led to conscious observers, and those observers are now using tools built from that same stardust to turn their gaze backward to ask how it all began. We are the cosmos thinking about its own origins. So what does this mean? It does not necessarily imply a guiding hand or a predetermined destiny. The path was chaotic, filled with false starts and catastrophic ends. Countless stars died sterile deaths, and entire galaxies may have formed and evaporated without ever giving rise to a single planet. But the potential was always there, written into the laws of physics. The force of gravity pulls matter together. Nuclear fusion in stars creates heavier elements. Those elements enable chemistry. Given enough time and enough cosmic real estate, these simple rules seem to inevitably generate complexity. We are not a miraculous accident, but a possible, perhaps even a probable, outcome of a universe that has the right constants and the right ingredients. Our existence is a data point in cosmic history, evidence that the universe can, under the right conditions, generate beings capable of understanding it. This final mystery, then, is not about a missing piece of data or a flawed simulation. It is about the meaning we derive from the story itself. The journey from the first stars to us suggests a universe that is inherently creative. The silence of the Dark Ages was not a permanent state, it was a prelude. The first light was the spark that ignited a chain reaction of creation that is still unfolding. When we look at the deepest images from the James Webb Space Telescope, we are not just looking at ancient galaxies. We are looking at our own deepest past, the earliest chapters of a story that leads, through an unbroken chain of cause and effect, to this present moment of curiosity and wonder. The greatest mystery of the first stars may not be how they formed, but what their formation set in motion, a universe awakening to its own existence, one question at a time. 30 profound mysteries, each one a gateway to the universe's deepest past. We have traveled from the silent collapse of the first gas cloud to the explosive death of the first star, from the clearing of the cosmic fog to the assembly of the first galactic cities. We have followed the journey of the first heavy elements as they became dust, then planets, and finally part of us. This is not a collection of isolated riddles. Every question about the mass of the first star, the timing of reionization, the origin of supermassive black holes, or the nature of dark matter is a single thread in the same grand tapestry. It is the story of how our universe grew up, transforming from a simple, uniform fireball into the complex, structured, and breathtakingly beautiful cosmos we survey today. For generations, these were questions of pure theory, confined to chalkboards and supercomputer simulations. We could imagine the dawn, but we could not witness it. That era is over. We are no longer just imagining the cosmic dawn, we are beginning to see it. The James Webb Space Telescope is our time machine, its infrared eyes peeling back the layers of time to reveal galaxies shining when the universe was a mere infant. Gravitational wave observatories are our cosmic ears, listening for the tremors from the first black hole collisions. Vast radio arrays are tuning in, hoping to catch the faint song of the first hydrogen atoms. These are not tools of passive observation, they are instruments of interrogation. They are turning philosophical wonder into hard, testable data. Each new image, each new spectrum, each new ripple in space-time is a piece of evidence in the greatest detective story of all time. The answers we seek will do more than satisfy our curiosity about what happened over 13 billion years ago. They will reveal the fundamental rules of reality. By understanding the first stars, we test the laws of nuclear physics in an environment we can never recreate. By mapping the first galaxies, we probe the nature of dark matter and the strength of gravity on the largest scales. By timing the cosmic dawn, we measure the very expansion rate of space itself. This journey into the past is paradoxically a journey into the most fundamental workings of the present. So stay curious. The next great revelation might come tomorrow in a data stream from a telescope a million miles from Earth, or in the subtle signal buried in the static of a radio antenna in a remote desert. The story of the first stars is our origin story. It is the prologue to every galaxy, every solar system, and every living world. As we continue to listen to the echoes of that first light and trace the shadows of those first giants, we are not just uncovering the history of the universe. We are discovering the context for our own existence, and in doing so, learning what it truly means to be made of stardust and to be the universe thinking.